On August 15, 1977, something incredible happened. For just 72 seconds, a radio telescope picked up a powerful narrowband signal from deep space. It was so unusual, so distinct from the background cosmic noise, that the astronomer who discovered it, Jerry Emin, circled the data on the printout and simply wrote, "Wow." That one word gave a name to one of the greatest mysteries in the history of science, the wow signal, and for over 40 years it has remained completely unexplained, until now. The signal was detected by the Big Ear radio telescope, pointed towards the constellation Sagittarius. It came in at a frequency of 1,420 MHz, which is hugely significant. That's the frequency of neutral hydrogen, the most abundant element in the universe. Scientists have long called this the watering hole frequency, a logical, universal channel where an intelligent civilization might choose to broadcast a message. The signal was 30 times stronger than the typical background noise, and its 72-second duration perfectly matched the time it would take for the telescope to scan past a fixed point in space as the Earth rotated. Every attempt to explain it as a satellite, an aircraft, or terrestrial interference failed. And most frustrating of all, when astronomers pointed their telescopes back to that same spot in the sky, they found nothing. The signal was gone, never to be heard from again. It was a one-time cosmic event, a whisper from the stars that left us with more questions than answers. Was it a natural phenomenon we just don't understand? Or was it truly a greeting from another intelligence? The data was preserved, but the mystery only deepened over the decades. Now, a controversial new theory is shaking up the scientific community. Astrophysicist Avi Loeb has proposed a stunning explanation that connects the wow signal to a completely different celestial object. He looked at the historical data and made a startling discovery. An interstellar comet now known as 3I Borisov was in that exact patch of sky on that exact night in 1977. Using precise orbital calculations, Loeb determined that the odds of this being a mere coincidence are less than 1%. This wasn't just any comet. It was a visitor from another star system, passing through our own. Could this have been the source? The theory is bold. It suggests the signal wasn't a broadcast beacon, but perhaps a targeted transmission from an object traveling with, or even part of, the comet itself. Think about it. An interstellar probe, using a comet as a shield or power source, sending a powerful burst of data as it passed through our solar system. To send a signal that's strong from so far away, hundreds of times farther than the Earth is from the Sun, would require an immense amount of power, something like a 2-gigawatt transmitter. That's the output of a major power plant on Earth. What kind of technology, what kind of intelligence could be capable of that? Loeb's hypothesis forces us to reconsider everything. It's not just about a random signal from a distant star anymore. It's about the possibility of a physical object, an artifact of extraterrestrial engineering that passed right through our cosmic backyard. This idea is, of course, highly speculative. Many scientists are skeptical, pointing out the lack of repeated signals and the fact that we can't go back and check. But the mathematics are compelling, and the coincidence is hard to ignore. So, where does that leave us? Are we on the verge of solving the 40-year-old mystery of the wow signal, revealing it as the first evidence of an interstellar technological artifact? Or is this just another fascinating, but ultimately unprovable, theory in the long search for extraterrestrial intelligence? The stakes are enormous. If Loeb is right, it would mean we're not alone, and that evidence of alien technology has been sitting in our archives for decades, waiting for us to connect the dots. It would change our place in the universe forever. The debate is just beginning, but one thing is certain. The wow signal is more intriguing today than ever before. Have you heard of the wow signal? In 1977, a radio telescope picked up a powerful, mysterious signal from space that lasted for 72 seconds and then vanished. It remains one of the most compelling pieces of potential evidence for extraterrestrial intelligence. But what if it wasn't just a random blip? What if we could trace it back to a specific object? Fast forward to 2025, astronomers discover a new interstellar visitor, an object from another star system, which they name 3-2 Atlas. Here's where it gets really strange. A team led by Avi Loeb decided to run the clock backward on Atlas's orbit. They wanted to know where it was on that exact night in 1977. The result was astonishing. On August 15, 1977, Atlas would have been right in the same patch of sky where the wow signal originated. Now, close in space is a relative term. The object's calculated position was a few degrees off from the signal source. But even with that offset, the probability of a random interstellar object lining up with the WOW signal's location on that specific date is less than 1%. That's like flipping a coin and getting heads 7 times in a row. Not impossible, but incredibly rare. Skeptics argue that orbital uncertainties could change these numbers, but the initial calculation is tantalizing. And it gets even more interesting when you look at the power required. To send a signal as strong as the WOW signal from Atlas's 1977 location, you'd need a transmitter with an output between 0.5 gigawatt and 2 gigawatts. That's the same amount of power generated by a large nuclear power plant. This wasn't some tiny beacon. It would have been an industrial-scale transmission. But it's not beyond technology we already understand. Most astronomers remain cautious, and for good reason. In a universe this vast, rare coincidences are bound to happen. But for Loeb and his team, this combination of factors, the orbital overlap and the plausible power requirement, is too significant to ignore. It keeps the debate alive. But the oddities of 3-2 Atlas don't stop there. Its journey through our solar system is just as bizarre as its potential past. Most interstellar objects that visit us, like Oumuamua, slice through our solar system at steep, random angles. They come in high and fast, then they're gone. Atlas is different. It's gliding through on the ecliptic plane, the same flat disk where Earth and all the other planets orbit the Sun. Its path is tilted just 5 degrees off this plane. Think about that. Out of all the infinite directions an object could approach from, Atlas chose a path that's almost perfectly aligned with our planetary highway. The odds of that happening by chance are about 1 in 500. It's moving less like a random cosmic drifter and more like something that belongs here. And the coincidences keep stacking up. As Atlas travels along this improbable path, it's set for a series of planetary near misses. On October 3rd, it will sweep within 29 million kilometers of Mars. By interplanetary standards, that's a close shave. Shortly after, its orbit brings it remarkably close to both Venus and Jupiter. The chances of a single interstellar object threading this kind of multi-planet gauntlet are vanishingly small. We're talking less than 1 in 20,000. Statisticians will tell you that rare events happen. But when so many rare events happen together, the ecliptic-hugging orbit, the string of planetary flybys, it starts to look like a pattern. Imagine shuffling a deck of cards and pulling the ace of spades 5 times in a row. You'd definitely start to wonder what's going on. Supercomputer simulations confirm this isn't normal. They've modeled thousands of hypothetical interstellar visitors, and almost none follow a path like Atlas. This object is a true statistical outlier. And finally, there's its appearance. The very first images of Atlas revealed something that defied all expectations. Instead of a typical comet tail streaming away from the sun, it had a concentrated glow on its sunward side. Observers are calling it an anti-tail. This bright spot on its front end couldn't be explained away as an imaging error or a camera glitch. It was real. What could cause this? A normal comet's tail is made of dust and gas pushed away from the sun by solar wind. An anti-tail points towards the sun, which is physically counterintuitive. It suggests that larger, heavier dust particles are being released, which are less affected by solar pressure and remain along the object's orbital path. But the brightness and concentration of Atlas's anti-tail are unusual. Is it possible that we're not just looking at a rock? Could this be a natural phenomenon we've never seen before, or is it something else? The strange orbit, the potential link to the WOW signal, and now this weird anti-tail, it all paints a picture of an object that is anything but ordinary. As Atlas gets closer, every telescope that will be pointed its way. Will we find answers or just more questions? The real test is whether we can detect any new signals from it, or if the WOW signal will remain a 45-year-old mystery. One thing is for sure, 3-2 Atlas has our attention. What it reveals could change our understanding of the cosmos forever. Something strange is visiting our solar system. It's called 3-2 Atlas, and it's rewriting everything we thought we knew about comets. The story starts with a simple picture. Imaging teams at Gemini South and the Very Large Telescope were looking at Atlas and noticed something odd. It had a structure, a kind of jet that was always facing forward, pointed directly along its path. Now, for a spinning, tumbling rock in space, that's incredibly weird. A forward-facing jet should be a fleeting, random occurrence, unless of course the object isn't tumbling. unless it's somehow tidally locked or actively keeping itself pointed in that one direction. For a natural object, that kind of stability is almost unheard of. Immediately, scientists were divided. Some argued it was just a trick of geometry, a fluke of our viewing angle. Others, however, whispered about something more radical, a controlled or at least non-random surface. The puzzle only got deeper from there. As Atlas raced towards the inner solar system, it started to shed gas. A lot of gas. At its peak, it was spewing out about 150 kilograms every single second. That's a powerful outflow, enough to blast away over 12,000 tons of material every day. In comet science, this kind of mass loss acts like a rocket engine. These jets of gas push on the comet's core, its nucleus, nudging its orbit ever so slightly off the path predicted by gravity alone. For almost every comet we've ever studied, even a little bit of this activity leaves a clear fingerprint in its trajectory. You see a slow drift, a subtle curve away from the clean, predictable path of gravity. But when dynamical modelers tracked 3-2 Atlas, they found nothing. No deviation, no drift. Its orbit stuck to the gravitational script with uncanny, almost unnerving, precision. This was a major problem. How could it be blasting out so much material and not feel a push? The only way the math worked out was if the comet was incredibly massive. The team ran countless simulations, testing every possible combination of size and density. They found that for anything smaller than about 5 kilometers across, the numbers just didn't add up. Atlas should have veered off course long ago. To balance the books, to explain why it was so stable against its own jets, the nucleus had to have a mass of at least 33 billion tons, and likely a lot more. This one calculation instantly catapulted Atlas into the record books. It is, by orders of magnitude, the most massive interstellar object we have ever detected. But the weirdness didn't stop with its motion. When spectroscopists pointed their instruments at Atlas, they were looking for its chemical fingerprint. What was this thing made of? Early spectra started circulating among research teams, and the results were baffling. The preliminary reports pointed to an atmosphere completely dominated by carbon dioxide, maybe as high as 95%. Meanwhile, water vapor, the absolute staple of comets from our own solar system, was barely detectable, registering at less than 5%. A ratio like that isn't just rare in our cosmic neighborhood, it's practically unheard of. As if that weren't enough, they also saw a steep rise in cyanide emissions and a pronounced green glow around the nucleus. These added to the growing list of oddities. But the real firestorm ignited when they looked at the metals. They detected neutral nickel glowing brightly in the comet's atmosphere. But iron, which in the natural universe is almost always found alongside nickel, was completely absent. In stars, where these elements are forged, nickel and iron are made in similar proportions. You just don't find one without the other in natural comets. This bizarre pairing-strong nickel, no iron, led to some wild speculation. The data hinted at a compound called nickel carbonyl, something more familiar to industrial chemists working in factories than to planetary scientists studying comets. One spectroscopist even described the chemical profile as looking processed, like an echo of something manufactured. Of course, others urged caution, pointing out that we can't completely rule out some rare, undiscovered natural chemistry. Then there was the nickel emission itself. As Atlas moved away from the sun, the nickel signal faded incredibly fast. It followed a mathematical rule known as an R⁹ power decay. This is an abnormally steep drop-off that our standard models of how comets work simply cannot explain. Why would it fade so quickly? One idea is that only a very thin, volatile-rich layer on the surface was being stripped away, and as Atlas got closer to the sun, this layer was exhausted, exposing deeper, different materials underneath. Others wondered if it was a sign of something even stranger, like selective outgassing or even an engineered release of material designed to produce exactly that curve. For now, the debate is wide open, but the stack of anomalies just keeps growing taller with every new observation. So here's where we stand. We have a massive interstellar object that appears to defy the laws of motion as we know them for comets. It seems to have a controlled orientation, it's unfathomably massive, and its chemical makeup is unlike anything we've ever seen in our solar system. The imaging analysts, the dynamical modelers, and the spectroscopists are all facing contradictions that our best models of natural comets struggle to reconcile. Is 3-2 Atlas just a 1 in a trillion natural oddity? A cosmic platypus that forces us to expand our definition of what a comet can be? Or is it something else entirely? The dossier is still incomplete. The crucial question is whether these paradoxes will dissolve as we get better data, or if they will only deepen as new findings come to light. The truth is out there, and with every observation, we get one step closer to uncovering the real story of 3-2 Atlas. It's a detective story playing out on a cosmic scale, and we're all watching, waiting for the next clue. October 3rd, 2025. Mark that date. It's a day circled on every mission planner's calendar, a moment that could change everything we know about our place in the cosmos. On that day, the enigmatic interstellar object, 3II Atlas, will sweep past Mars at a distance of just 29 million kilometers. For planetary science, this is a fleeting but absolutely critical window. The race is on. Mars orbiters, including NASA's MRONES Tracegas orbiter, are being prepped for an immense challenge: to capture high-resolution images of an object barely 5 to 7 kilometers wide, hurtling against the deep, dark backdrop of space. Technical teams are running non-stop simulations. They're dealing with an object that, even for our sharpest cameras, will appear as less than 1/100th of a pixel. High RIC, the most powerful camera we have at Mars, can resolve features as small as 0.3 meters on the Martian surface. But at this vast distance, Atlas shrinks to near invisibility. The mission planners know the odds are long. Yet, the opportunity is simply too rare, too important to ignore. For ground controllers, it's not just about getting a clear picture. Tracking a fast, dim target from a moving orbiter requires pinpoint precision and split-second timing. Even detecting it as a faint point of light would be a monumental victory. It could help us refine its position, its velocity, and check for any unexpected activity like jets of gas, fragmentation, or a trail of precursor debris. The imaging window itself will last only a few precious hours. Data downlink schedules are being cleared, and real-time analysis teams are on standby, ready to process whatever information we get back. The ambition doesn't stop at Mars. Proposals are circulating for even more audacious plans. The Juno spacecraft, currently orbiting Jupiter, is being considered as a potential asset for a March 2026 intercept, if its trajectory and fuel budget allow. But mission engineers are weighing the risks. Juno's cameras, designed for imaging Jupiter's auroras and atmosphere, lack the sensitivity to resolve a small, distant interstellar object. ESA's JUICE and NASA's Europa Clipper face similar limitations. At 29 million kilometers, Atlas would be smaller than 1/30th of a pixel in their viewfinders. Any Comar jets would just blur into a noisy smudge. The operational verdict from the experts is blunt. No current spacecraft can deliver a resolved, detailed image of Atlas at this range, so our attention is shifting. Hope now rests with the Galileo project and our most powerful ground-based telescopes. Using advanced adaptive optics and rapid response photometry, we have our best shot at detecting any outbursts or directional jets, especially if we can coordinate these observations with the Mars flyby. The criteria for what would be a significant detection are incredibly strict. We'd be looking for symmetry, jets aligned with its axis of rotation, or evidence of structured fragments, clues that could help us distinguish a natural comet from something engineered. For now, the focus is on a single goal: collect every possible photon of light from this object before it slips further from our grasp. The October 3rd window is narrow, and the technical odds are stacked against us. But the potential payoff, a direct glimpse at the most massive interstellar visitor ever, recorded, is keeping every console lit and every scientist working through the night. Then comes October 29th. This date draws a hard, dark line across the calendar. On this day, 3II Atlas will disappear behind the sun, completely lost in its glare, beyond the reach of every Earth-based telescope. The blackout will be absolute. Even our most powerful space telescopes, Hubble and the James Webb, will be forced to wait. Their safety protocols strictly prohibit them from observing anything so close to the solar furnace. The result is a total communication silence that will stretch from late October into early December. And this radio silence happens at the most critical point in the story. This is where propulsion specialists enter the conversation with calculations that have become central to the entire debate. If Atlas were to perform a maneuver, this solar conjunction would be the perfect time to do it. There's a principle known to every interplanetary mission designer called the Oberth effect. It allows for a massive change in velocity, we're talking 30 to 40 kilometers per second, if a propulsion burn is executed at perihelion, the closest point to the Sun. For a natural comet, such a maneuver is impossible. But for an advanced probe, the blackout provides the perfect cover. No instrument on or near Earth could track such a trajectory change in real time. We would only know after the fact, when the object re-emerges weeks later. Only then can its new orbit be remeasured and any deviation detected. The decisive test will come in late November or early December. That's when orbital dynamicists will compare the new trajectory to all the previous observations. If it's a perfect match to the pre-blackout path, it would strongly favor a natural explanation. But any significant deviation, especially one requiring a huge change in velocity, would force us to reconsider every single assumption we've made about this object. This is why SETI directors and risk analysts are framing the situation as a yellow alert scenario. The stakes couldn't be clearer. If Atlas emerges from behind the Sun on a shifted orbit, the case for it being an artificial object strengthens dramatically. If it continues on its predicted path, the stack of anomalies shrinks, and the evidence points back towards a rare but natural phenomenon. To ensure transparency, observatory teams have already pledged to share all positional updates in real time, minimizing the risk of rumors or misinterpretation. For now, the scientific community can only wait. Our instruments sit idle as the object passes through its period of maximum uncertainty. The outcome, whether it's confirmation or refutation, will define this incredible story for years to come. It is crucial to remember that as of today, there is no direct evidence linking 3-2 Atlas to an artificial origin. Many of the initial, exciting observations remain unverified or even classified. As missions prepare for the October 3rd Mars flyby and the October 29th solar occultation, the testable claims are standing clear. The data we collect in the coming months will determine if this is a truly unique comet, or something entirely unprecedented in human history. For now, much like the famous WOW signal, 3-2 Atlas remains a profound scientific question, grounded in numbers and patiently awaiting answers. Thanks for watching. Be sure to subscribe for more updates on this developing story.